exciting journey, blah, blah, blah. Let's pray. Lord, I just ask that you would show more of you in our class today. Help us to see you in this content. Help us to understand this crazy stuff. In Jesus' name, amen. So today we embark upon chapter 6, chemical bonds. When I looked into my old notes on chemistry class from the first year I taught it, we were at chapter 3 at this point in the year. So we have flown a little bit faster than normal through this content. But today's content and this chapter's content is quite exciting and very important. On a scale of 1 to important, this is all of chemistry. So, that was gross. So, I would highly encourage the paying of attention. In fact, if you can pay multiple attentions, that would be great. So, there are 3 classifications of chemical bonds, and they are as follows: covalent, ionic, and metallic. Covalent, ionic, and metallic. What are covalent bonds? Covalent bonds are bonds that are between nonmetals. And they are characterized by like a sharing of electrons. I hear voices. I think my computer is playing music. Okay. So, covalent bonds are bonds made between nonmetals. So we're talking oxygen, fluorine, sulfur, like those guys up there, upper right-hand corner. Also hydrogen, and it's like a sharing of electrons. So you have extra electrons hanging out and they are shared. That's what we're going to spend most of our time today on. Ionic bonds are generally between anions and cations. Anions and cations. So anions are, I always mess this up. Should I check the light before I teach it wrong? I was right. Okay, anions are negatively charged and cations are positively charged. If you are cat people, this will make sense to you. If you are not cat people, it will be the exact opposite of what you think would be true. So that is that. I need more lotion because my hand is drying out. Okay. So basically, you're going to have some sort of metal with some sort of non-metal. That's generally an ionic bond. You can have a completely covalent bond. You cannot have a completely ionic bond. So ionic bonds are where you're completely giving over, like a perfect ionic bond would be you're completely giving up electrons. That's just not the case. Okay, you'll never perfectly do that. There will be some sharing. They're like orbiting the nucleus anyways, so it's like hard to get rid of them. So anyways, that's ionic. And then metallic is a metal plus another metal. And this generates something called an electron cloud. So you have a bunch of metals together, and that's a metallic bond. So those are the 3 that we will be discussing at length, or ad nauseum, if I may. I feel like I ordered markers and they never arrived. I must make a note. Markers. Okay, there we go. So let's talk about the octet rule. The octet rule is simply the following. Do I want to do this nicely? Okay, oct means 8. So you want 8 electrons. And specifically valence electrons. The octet rule says that if you are an ion, if you are an element, or if you are an atom, you want to have 8 valence electrons because that completes your outer orbital. And then you're a happy camper. We've discussed this ad nauseum, or at length to the point where we are nauseated, right? So we don't have to review this. But you want 8 valence electrons, okay? So the octet rule does apply primarily to nonmetals and your alkali and alkaline earth metals. It does not apply to transition or those two guys at the bottom, the lanthanides and actinides, okay? Transition metals, they do weird things. Lanthanides and actinides, they do weird things. So they're not really gonna like desire that perfect 8 as much as transition metals, nonmetals, alkali metals, alkaline earth metals, even those weird metals, the post-transition metals, those guys like it too. So I'm gonna add one in here and it's gonna mess up all of your notes. Is that legible? Absolutely not. So, what am I saying? Everything wants that outer valence electron or orbital filled because they want to get to the noble gas configuration.
Post-transitional?
Post-transition metals. So we want a noble gas configuration, and then we're happy. Nonmetals, alkali, alkaline earth metals, post-transition metals, not transition, lanthanides, actinides. You guys got this. I'm preparing you for college. You just have to write everything as quick as you possibly can. And then some kids are like, can I bring? No, sorry, they don't make that noise. They're like,
Now they do.
No, they do. Okay, so they make this noise, and then they're like, can I please record the lessons and then re-listen? Ain't nobody got time for that. Like, you can't sit there and like, I'm going to re-listen to this lesson. Like, do it the first. Anyways, so learn to write quickly. Moral of that story. Okay, so we want 8 electrons. Sound good? So let's dive in a little bit to how we're going to figure these things out. And the way we're going to figure these things out are called, I should talk about that. Skip. All right. It's not bad. I was like on a roll. I knew where I wanted to go. Okay. Let's talk about polarity, even though I don't want to talk about it. So the reason why bonds happen is if you imagine like a magnet, right? You have your positive end of the magnet, you have a negative end of a magnet, right? And then if you were to put it up against the positive end of another magnet, they would repel, right? But if you have a magnet that is like facing that way, then they would attract and they would bond together, right? Those two magnets would be pulled. Did you draw my magnets? Come on, man. I want to see beautiful pictures of magnets. Here's your pro tip. If you ever stop writing, then you're doing it wrong. Keep writing. Just keep writing and then keep writing more and then keep writing until like your hand is like, oh, my hand, and then keep writing. Okay. So much like magnets where they will draw together, we have atoms that tend to be more positive in some places. And then we have other atoms that tend to be more negative. And what will happen is that they draw together. So within oxygen, you have a bunch of electrons on the outside, right? There are certain parts of your electron cloud which are more negative. Sorry, that would be over here. And we'll want to attract certain other areas that are positive. And so these positive sections will attract the negative sections and they will bond. Okay? That's how bonding works. Now, we talked a little bit about electronegativity. What is electronegativity? It is, I will write it for you. Woo! It's the measure of an atom's ability to attract electrons to itself. Keep writing. Keep writing. You must keep writing. Never stop writing, okay? Just keep going. You have it? You're done? But I'm writing right now. How could you be?
Because I already have.
Oh, because I'm. But it flows with this part of the notes. Like you just keep writing, okay? Everyone keep writing. Okay, so the more electronegative something is, the more likely it is to attract something that is less electronegative. So hydrogen wants to get rid of its electron, so it is very low electronegativity. Oxygen wants to, and then it's a happy camper, so it is highly electronegative. Okay, it wants those extra electrons. Hydrogen wants to get rid of them, and so it's a happy camper. Flipping page. I'm glad I discussed that. Now, are you guys doing okay over there? All right. The disparity in electronegativity will dictate what type of bond you form. So, we talked about covalent and ionic bonds. Covalent bonds, generally between nonmetals. Nonmetals are going to be similar in electronegativity. Why? Because they're in the same column, or at least they're on the same part of the periodic table. So these are similar electronegativity. I don't know why I left so much space. Ionic bonds have high differences, or a large difference, in electronegativity. So, which one do you think forms stronger bonds? Which one's going to form a stronger bond?
Covalent.
So, if you take two magnets and they're of similar strength and put them together, as opposed to a magnet where, like here, we're talking you have like a magnet that's positive, and it's kind of still positive, but they're willing to like be around each other, as opposed to one where you have like a very negative one and a very positive one. Which one is going to pull together more? Ionic, right? So ionic results in a stronger bond. What do these ones normally do? Like if you have two kind of weak magnets, have you ever tried putting them together? They repel, but then what happens? Like they usually, like you have one magnet here, you have one magnet here. After you push them together long enough, what happens? They usually like, and then attach, right? Somehow. Like some weird flip happens and then they like lightly attach along the edge, but not really like strongly bonded. So ionic are always going to be the stronger of the bonds because you have a high difference in electronegativity. So mean today. Man. All right, so back to what I wanted to talk about. We are going to talk about Lewis dot structures. There was some guy named Lewis, and he figured most of this out. Now, part of this is review. So if I were to ask you to put the valence electrons around oxygen, you would look at your periodic table, go, oh, oxygen has how many valence electrons? Everybody?
6, right?
Oxygen has how many valence electrons?
6.
6. And then you would draw the little dots, right? 1, 2, 3, 4, 5, 6. Right? Happy campers?
Yes.
Maybe? How many does it need in order to fulfill the octet rule?
2 more.
It needs 2. Now, here's what the cool thing about a Lewis dot structure tells us. It gives us a feel for how, within covalent bonds only, than covalent only, it gives us a feel for how it's going to fulfill those extra bonds. For example, with water, hydrogen has how many valence electrons? No. 1. Right? Because it's element number 1, so it has 1 electron. And if I have another hydrogen over here, I can move these dots wherever I want, which is great. Now suppose I have oxygen here with its 6. The Lewis dot structure for water looks like this. Watch this. So you'll notice that I kind of broke up that last pair. And I'm going to make a bond between these 2 electrons. So now they're going to be shared between these 2 atoms. These 2 electrons are also going to be shared. What does that do for us?
It was 8.
That gives oxygen 8 electrons. Because it's got 2, 4, 6, 8. How many does hydrogen get? 2. Is hydrogen happy with 2? Hydrogen's happy because 2 electrons is enough to fill that outer orbital, the 1s orbital. So hydrogen is happy with 2, oxygen is happy with 8, and you get water, okay? Which is covalently bonded, surprisingly enough. Okay? So we're going to be drawing these out to get a better idea of what's going on in various compounds. So, let's start with our diatomic elements. Remember how I told you there's some elements that share or that bond to themselves? You're like, what? And I was like, yeah, like H2, that's just hydrogen, right? How does that work for hydrogen? Well, let's draw the valence electrons on our hydrogen atoms. How many valence electrons does hydrogen have? Everybody? 1. Why? Because there's only 1 electron for hydrogen in its ground state. So this hydrogen has 1. This hydrogen has 1. If they bond, they're sharing each other's electrons. But now we have each of them with 2, so this becomes a stable compound, right? They're no longer looking to bond with other things. They're no longer looking for those extra electrons. They found them, okay? It's not the strongest bond ever. If you get a bunch of H2 everywhere, it will bond with other things and break off this bond. But for now, that's a good bond. It's a steady state. Okay, let's go for nitrogen. How many valence electrons does nitrogen have? Look it up. Periodic tables. Come on, guys. You're in chemistry class. You're expected to have this stuff.
7.
Nitrogen has 7 valence electrons. I disagree. Strongly. How many? Okay, it's a number between 1 and 8. 5.
Oh, I see. Now.
Count the first 2 columns, and then nitrogen is 3 and do I believe that? Yes, I do. And you get 5. Okay, so that's 1, 2, 3, 4, 5. This one has 1, 2, 3, 4, 5. Now, what nitrogen does, because it wants how many valence electrons?
3.
How many does everyone want?
8.
8. It's actually going to do some weird things. So obviously it shares this one. Does that give it 8?
Nope.
That gives it,
5.
oh dear,
6.
2, 3, 4,
Yeah,
5,
6.
6. Okay? Is 6 8?
No.
No, so it needs to share more. Is that 8?
No.
2, 4, 5, 6, 7. So this one actually makes a triple bond with itself. And you get 2, 4, 6, 8. Gross?
Oh,
I don't know. Makes sense, but then I have a question, mister.
Yeah.
Oh, never mind.
You just said you got a question.
Well, I was gonna ask you then what would happen if like a number had like a greater number than 8, but then you just said that like 8 is like it's like cut off number.
Yeah, you really don't. Some of the transition metals and stuff will do weird things and get more than 8. So it happens, but then it flows into the d orbital or the f orbital. But for non-metals, you won't go there, generally speaking. Cool. Good question. So what else do we know is diatomic? Our favorite element. We enjoy it. We need it for life.
Oxygen.
Oxygen. How many valence electrons does oxygen have? From over here, we remember it.
6.
6. So if I draw out the 6 dots here, okay, there are no unpaired electrons, right? Like they're all in pairs. So it's going to steal 2 of these and make bonds with itself. So we get a double bond here. Each bond, remember, those electrons are shared. So for this oxygen, I have 1, 2, 3, 4, 5, 6, 7, 8. They're shared between all of the atoms. So it's as if this guy doesn't exist and this guy has 8. But it's also as if this guy doesn't exist and that guy has 8.
So you're not adding anything, you're just sharing.
They're just sharing. Sharing is caring. It could be fun. Usually not. Like when someone has to tell you to share, that's usually like, ugh, I have to share. Like, or like sharing the gospel and you're like, to share the gospel. And it's like you have this great, like, you have this great thing and you're like, no, I'm not going to share my electrons, right? Like, I have salvation ready to share with you. And then it's like, nope, not going to happen. You know, like, how selfish, man. Anyways, but sometimes it takes a little bit more work. The way these actually work is that these electrons like orbit both in some weird path. It's weird. So you can look up videos on that on your own time. So the entire list of diatomic elements that will do this are as follows. You should know this. H2, N2, O2, F2, Cl2, Br2, I2. These, you will notice, are all a member of what family?
The first. No.
What family are those
Oh, the
in?
diatomic.
Good guess, though.
The post.
Nope.
No, they're in the first group. I can't remember what it's called.
Oh dear. What's the last column before the noble gas is called? The halogens. That's right. That's somebody who took notes there and referenced them. Many of you took the notes and then you just left them there. You're like, oh, I don't know. And then it's like, oh, it's on the last page. Reference your notes. It is important. True story. So these are halogens. We already said that the halogens are highly reactive, so we're not surprised that they would form covalent bonds with themselves, right? They just need that one extra electron. So they're like, please give me that extra electron. These guys are a little bit more surprising, but not too surprising. So let's talk about Lewis dot structures. The idea of this is that we're going to take, I mean, these are kind of boring because they're all the same, but we're going to take different elements, put them together, and see how those bonds will form. We do have options for single bonds, double bonds, or triple bonds, but the idea is that each atom should add up to how many electrons? Micah?
Huh? 8.
8. That's right. 8 electrons, including shared ones. So here is That's annoying. Okay, here's some guidelines, and then I'll teach you how to actually do it. We love guidelines. When we write them ourselves, and when other people write them, we're like, oh, I have to read this, right? So, guidelines. Number 1, it only works for covalent. Number 2, electron sharing occurs when one nonmetal bonds with another, or when two identical nonmetals bond. Each nonmetal generally forms covalent bonds to achieve 8 electrons. Okay, hydrogen is the exception. Hydrogen wants 2 electrons. That's weird. Cool. Electrons are generally shared in pairs. So everyone has a part to give, right? It's not like one is, they're all nonmetals, so they all have a bunch of electrons hanging out there. So they have electrons to share. Pairs will be very important. You will see that. Okay. Polyatomic ions. Poly meaning many, atomic meaning atoms. Yeah. So we're going to have polyatomic molecules which contain 3 or more atoms. They have 1 or more central atom. That says central. That says atom. Central. There we go. That's that. Okay. And that's fine. Okay. So those are guidelines as we draw these Lewis dot structures. Now, here are the steps. So, step 1, you are going to draw out the valence electrons. Okay? Electron dot for each element or atom. So, like we did here, we drew the hydrogen by itself with 1 dot. We drew the other hydrogen by itself with 1 dot. So at this point, if we were doing water, you would draw out hydrogen dot oxygen, like that. So that's what your picture would look like. Question?